Okay, good afternoon, everyone. Welcome once again to today's seminar. Our presenter will be Blaž from Slovenia. So Blaž, the floor is yours, please.
Okay, thank you, Daniel. So good afternoon, everyone, and thank you for joining this webinar. And as Daniel already said, my name is Blaž Vičič, and I work at Seismological Office of Slovenian Environment Agency in Slovenia, in the capital of Ljubljana. Today, I'll be walking you through how we use relocated seismicity to map active faults, essentially how we turn some clouds of events, cloud of earthquakes into slightly more sharp and sometimes interpretable fault structures. And we will cover the full pipeline that is used for this. So we will go from kind of sources of errors that attribute how well we are able to locate seismicity, and then to earthquake location uncertainty, and all the way to some advanced methods that are used to overcome these problems. So let's start at the beginning. So in this part one, which deals with the fundamental limitations, we will face problems with sources of errors in the earthquake location. Yeah, so first we need to understand what makes our locations poor or not so poor. And then there are three main culprits for this. So first of all, the geometry of our seismic network, the quality of our phase peaks, and the accuracy of our velocity model that we use for location of the earthquakes. So first we will look at each of those in turn and say a few words about that. So what do we mean by resolution in earthquake location? So the resolution is ultimately limited by two categories of errors. So on one hand, we have this epistemic uncertainty, which comes from our imperfect models. So basically, when we are talking about, let's say, velocity model, so it comes from those and from our incomplete knowledge about the region in general. So as I said, you can think of simplified velocity model or an uncalibrated instrument also. Sometimes the instrument brings the problems. Maybe we have timing errors in our seismic stations or something like that. The main point here is that this epistemic uncertainty is reductible. So if we make our models better, if we collect more precisely our data, we can reduce these errors to minimum. And then on the other hand, we have this aleatory uncertainty, which is basically kind of randomness. It comes from things like ambient seismic noise, which is caused by wind, ocean waves, human activity, and we cannot remove it. So no matter how good our velocity models are, no matter how good our instruments are, there is always some noise inside of our data. So this really affects waveform peaks. So when we are looking for P and S arrival times, we can make big errors just because the presence of such noise. But this can all be minimized through the steps of the earthquake relocation. So one thing is also what we need to do is we always have to quantify these errors, all these uncertainties, because when we show our earthquake catalog, we want to also show what are the estimated errors, not just the locations of the earthquakes. So the first major source of epistemic error is the network geometry, specifically how our seismometers are distributed around the earthquakes that we are interested in. So the most important metric here is the azimuthal gap, which is the largest angular opening between the neighboring stations as seen from the earthquake's epicenter. And as a rule of thumb, if the gap is larger than 180 degrees, then the horizontal location will be degraded severely. So the quality will not be very good. this means that not enough stations recorded such an earthquake. Then another problem that comes from the seismic network is the depth, which is kind of a tricky problem in earthquake seismology. And to get a reliable depth estimation, we need to have at least one station that is in a distance less than or equal to the depth of the earthquake, so the hypocenter. So you can think of this as if you have an earthquake at 10-kilometer depth, then the stations need to be within 10 kilometers away from this earthquake to get a good quality depth estimation, but this is normally not the case. And then another problem that comes from the networks is that if your stations are outside of the just a second. Okay, I have the pointer. So if our earthquake is away from the station slow, you can think of it happening somewhere offshore, maybe in the sea, then the locations will not be constrained well. So let's say if the earthquake happens here and all the stations are away from the only one side of the earthquake, then the earthquake will be pulled toward the stations and you will get very bad locations for it. What we can do regarding this, so the red triangles that you see here, these are the stations located in Slovenia, and there are some earthquakes happening here, but all our locations estimations are somewhere here, so the location is pretty bad. So how we solve this problem is we have access to networks from neighboring countries like Italy, Croatia, even Austria and Hungary, and we can use in our virtual network those stations to get better constraints on the earthquakes that happened outside of our network. And this is quite important thing to do, otherwise we can get quite bad locations. Then next source of error is comes from the phase picking. So the process of identifying the exact moment when a seismic wave arrives to the station. Even if we have very small timing errors, this will compound very quickly. So you can think of error, let's say for a P wave arrival, errors normally are around 0.05 seconds, so really small. For P, and for S slightly larger, around 0.15 seconds. These are realistic numbers, but these already introduce errors that can be several kilometers when we are using the standard linearized inversion. So there are several causes of picking errors. Of course, human analysts are subjective and can suffer fatigue. You know, there is a aftershock sequence or a swarm sequence. You have thousands of earthquakes. It's just impossible to pick the phases of all these events without starting to do some silly stuff. And how other things that also can quantify add to this error is how the waveform looks like. So if we have emergent offset, you can see here the wave is just slowly going up. So this means that we are unable to really put well-constrained P arrival time, or sometimes this is normally for S wave. It's much harder to recognize them, or if we have a lot of noise in the data. So it's very, very hard to do this. Luckily, we have algorithms that do this automatically, which I will discuss on later. Then the third and arguably the most important source of errors that come to our modeling location of the earthquakes comes from the velocity model. So the vast majority of routine earthquakes, earthquake catalogs today will use 1D velocity model. So we assume seismic velocity only varies with depth, not laterally. And this is a massive simplification. As you can see here on this image, if we use, this is a region of Slovenia, and if we use a 1D velocity model, we will get big errors, because you can see that on the western side, velocities are much higher than on the eastern side of Slovenia. So there is if we don't use the 3D velocity model, our estimations are much worse. So because the Earth has fault zones, sedimentary basins, we can have slow velocities or fast velocities in subducting slabs, let's say. So a lot of lateral and vertical heterogeneities. So 1D model will completely ignore this, and we are unable to really locate well. So the consequence of this 1D velocity models is that we have systematic travel time residuals, and when you can think this as if you have a basin and low velocities, the earthquakes can be located much deeper than they should be. So in the part 3 and 4, I will show you how this is also corrected and what can be done, even if we don't have a lot of good data sets to use with. Okay, so then next part, this will focus on seismic phases, basically on the picking of the seismic phases and association of the seismic phases. So how we know which of the seismic phases P and S arrival times are from one earthquake and from the other earthquake. Because this is very important, otherwise also we get wrong locations. So as you know, every earthquake radiates energy in the form of seismic waves. So the most important for location are P and S wave. And the time difference between the P and S wave on one single station is directly related to the distance from station to the earthquake. So the challenge here is to detect and accurately time these arrivals, especially for small earthquakes in noisy environments, or if earthquakes are overlapping, if two earthquakes happen very close in time. So all these things will contribute to problems in our phase peaks and then also earthquake locations. So here on this picture, you can see this is a sequence that happened last summer in Mediterranean Sea. So there was a volcanic activity, and there were thousands and thousands of earthquakes that happened in just a couple of days. And if we would tag this manually, you know, if people would be designated to hand-pick phases, this would take weeks and months. Not possible to do this by hand. And as I said, luckily we can use algorithms to detect these P and S waves. So the basic one, I'm sure you know, everyone knows about this. So the classic approach to phase detection is the so-called STA-LTA trigger. So basically a short time average over long time average ratio calculator, which tells you where a seismic wave is coming to your station. So you can imagine this window here, this is a short-term average, this is a long-term average, and when we get to our phase, the ratio between them will arise, and we can declare, okay, we have a P wave here. The concept of this methodology is very nice because it's very fast. It can be even run on a single station, on the hardware of the station for the triggered recordings. It's fast, it's used, I would dare to say, in every seismological office in the world. But it has its own problems. So let's say, normally it's very good for detection of the P wave, the first one. Then for the S wave, it already has problems because the short the long-term window will be full of this noisy data now, and the ratio cannot become very high. So normally we get much lower spikes for the S wave than for the P wave. And if there is a lot of earthquakes, then the algorithm cannot work good anymore because of the same problem, because we have a lot of amplitude data that affects our long-term average window. So as I said, the problems are swarms. When we have a lot of earthquakes, aftershock sequences, it's the same as for the manual P and S arrival times. In recent years, the modern phase picking has been revolutionized by the deep learning methods. So rather than looking at these energy spikes from the STA, LTA windows, machine learning models have learned to actually shape P and S wave arrival, so from the millions of labeled seismograms. So basically people did, when they were teaching the algorithms how to identify P and S wave, they labeled seismogram, this is a P phase, this is an S phase, and then they fed this to machine learning model to get something that is now able to detect these P and S arrival times. So the two most widely used architectures are the so-called PhaseNet, which is based on UNet architecture, which was originally actually developed for the biomedicinal imaging, and it uses some encoder-decoder structure to classify every sample in the waveform, outputting a continuous probability for P and S arrival. So you can see here, this is our raw recording. These are the energy STA, LTA envelopes. And then this is the output of the machine learning algorithm, which gives you probability for P and S. So you see that looks kind of similar to STA, LTA, but gives much more clear arrivals. So then the second commonly used is EQ transformer, which adds some few new features to our machine learning model, like global attenuation mechanism and some other things. So importantly here, now we don't have the timing of P and S arrival time anymore, but we get a probability distribution where the P and S is. And this is then easily something that we can use for the location of the earthquakes because it will give us better constraints. These machine learning pickers can do much more than just give you the P and S wave arrival time. It will also tell you if your part that you're looking at is noise, not an earthquake at all. And then it will give you polarity of the P wave arrival, so you can use this for focal mechanism. And it can also give you some source parameters like real-time magnitude and hypocentral distance from the station. So on the modern computers, this detection of earthquakes using machine learning runs very fast. So you can, in a couple of hours, you can scan years of data and get very good results. The only problem is that training such a model, it's not so easy. So you need to have GPUs or HPC computers to really train your models. And what you need to be aware of is that if you take one model generated, I don't know, in California, apply it to Rwanda, the results may vary. So you will get, for sure, detection will work very well, but it's even better if you take your earthquakes that you detected using your own network, relearn the model. So now it has knowledge about the Californian events and also the Rwanda events, and then the results are even better. There can be some artifacts like windowing artifacts, which is a problem during swarms or dense aftershock sequences because we use the fixed window approach, and this can split one event into two windows, and then this can make some complications. And another thing that you need to be aware of is this false confidence, because when you look at the this P and S arrival times, you can say, okay, this is really good, it's working as it should, but maybe you still need to check a few of the events that you're not picking wrong things. what can you also... There are also models that will denoise your data. So let's say you have a very noisy environment or maybe an aftershock sequence. There's a lot of noise from the aftershocks. Some models can remove part of this noise, and then you can pick the phases much better. I think that this could be also used, let's say, for volcanic monitoring. You can remove the volcanic noise and pick the phases much easier. Okay. And then when we have all these P and S arrival times, what we are left with, we need to say, okay, these P and S arrival times are from this earthquake, and these P and S arrival times are from another earthquake. So when we have a sparse catalog, so not many events, this is quite easy. You know, you can grid your area into sources and get P and S arrival times to each of the sources. So it's easy to do this. But as soon as we have, 1 million or more peaks, because we are working with a large data set, or because there is a swarm activity going on, this becomes very problematic. So there are, for example, what I'm showing you here, this is a so-called gamma mixture model associator, which borrows from the deep learning methodologies and can be very fast to associate phases to. I will not go into details, but just so you know that these steps are today very, very fast to perform on any kind of computer. Okay, then when we have all these things, so P arrival times, S arrival times, all the knowledge about the Earth structure for the region of interest, we can go into locating of these earthquakes. So the traditional approach to earthquake location, we know it as a Geiger method, will linearize the relationship between hypocenter parameters and the travel times using some this called Taylor series expansion. It's very fast and it works very well near a good starting solution. A problem that that we have here is that this methodology requires initial guess. So we need to say, okay, I have all these P and S arrival times. My earthquake happened here, and then we explore the space around this initial location, and we get the real location. So if our initial guess is not good, then even the final result is not okay. And we can easily get stuck in a local minimum when we are exploring this space and get completely wrong location. So using these linear approaches quickly motivates us to do more probabilistic approach, which will explore all the entire solution space rather than descending towards a single point where the earthquake would happen. So we can explore this as in the deterministic or a probabilistic way, and of course today if we do the probabilistic way, this is the really only way that we can report earthquakes. So the deterministic approach will say, okay, where is the earthquake? And the probabilistic way, it asks, like, where could the earthquake be? So in the deterministic way, we only get a point. These are two events somewhere in space, and we report their location and their error bars. But these errors that are given to this location, this is still normal Gaussian distribution, nothing more. But in the probabilistic way, because we explore the space fully in 3D, our distribution is not Gaussian anymore, so we can easily find where is a better, larger probability for earthquake to happen, and we can report all this PDF as a solution, not just a point. And then when we are exploring in a probabilistic way how this is done, we can look at grid search methodology. So basically we divide our space, 3D space, in many small points and check each of them, what's the probability of the earthquake to happen there. Of course, this is not okay, because if we are looking at a very large area and we are interested in a grid size of 100 meters, our computers will hardly be able to get the solution of where this earthquake is in quick time. I mean, it will take days to get location. So there are better, smarter way. This, let's say, adaptive octree search, which is implemented nicely in a non-in-lock software by Anthony Lomax. So basically what we do here is that we split our space in very big grid. So let's say 5 by 5 kilometers. And if our location is inside of this grid, we then make the grid here smaller, explore this space, and in next space even smaller one, and so we get down to the location of our event. So we don't have to explore full space, but just part of it. That's why everything is much faster and can be easily done on any computer. Then we have the limitation of travel time only location. So what I was discussing now with you, what I was telling you now, this is purely travel time location. But of course, we need something more. Let's say, if we are only looking at the travel time in cases like this, where we have in 3D velocity model higher velocities and then lower velocities and again higher velocities, our locations can be quite bad. But then if we use something more like more physics supported stuff like wave for cross correlation, we can get a slightly better location for this. So the location in when we are dealing with velocity model unknowns, one approach is to calculate so-called source-specific station terms, which I will explain more in detail in next slides. And this allows us to model also the unknowns in our velocity model. And then for slightly going from absolute locations to relative locations, we can use the cross correlation of the waveforms. You can see here, these are hand-picked waveforms on the P arrival, and you see they do not look very similar. But if we cross correlate them, we can see that they stack completely well, so they look all the same. And this is the information that we can use in location of the earthquake later. Okay, so first, let's talk about this source-specific station terms, or in short, SSST. This is an elegant workaround to the 3D velocity model problem. So what you normally have, I mean, you have a 1D velocity model, which can be problematic from what I told you before at the beginning. So our 3D Earth does not actually look like as our 1D representation. So we can use these source-specific station terms to overcome this. But if our initial data is the 3D velocity model, so if we already have a 3D velocity model, this SSST still gives us better results because it can still model some unknowns that are not shown in our 3D velocity model. So here is the idea how this works. Instead of building a full 3D velocity model, which requires enormous effort from our side and from the data side, we can learn how wrong our 1D model is at each specific station source region combination. And then we do correction for these things. So you can, here in this picture, you can see that after these SSST corrections, even if we use a 1D velocity model, we can map some areas where maybe our timing is always faster than the real P arrival times, and some areas where the arrivals are slower. And we can use this to map our 1D velocity error in 2D or in 3D, and then get much better final results for the location of the earthquakes. Normally, this SSST is also done in iterations. So first we explore grids in higher, larger kilometers, I don't know, 5 by 5 kilometers, and then we go to 1 by 1 kilometer and so on. And this SSST is already implemented with the non-in-lock software, so everyone can easily use it with their studies. Another thing that we should then do are these waveform cross correlations. So the two earthquakes that occur on the same patch on the fault will produce nearly identical seismograms at each station. So these events are called multiplet or repeating earthquakes, and the waveform of such an earthquake will look almost the same. So just there will be slight shifts in P and S arrival times that can be used for better constraining the location of this earthquake. So knowing these shifts from the cross correlation, this gives us a relative time difference between the two events. And this can be used to add or remove from our peak. And when we use location software like non-in-lock, we can get then much better results. So these cross correlations are also implemented in non-in-lock software. So we can say, okay, if the waveform of some events that we are looking at is more than 90% similar, this will be forced together and the relative location will be calculated for them. Then, of course, you may know there is also software like HypoDD. The difference is that HypoDD will give you deterministic relative locations, while the non-in-lock with SSST and cross correlation will give you absolute and relative locations. So then depends what you are interested in. If you are only looking at a single sequence and your location is very well monitored, so you have many stations, you might go for the HypoDD way. But if your area is not so well monitored and you are interested in more large scale geodynamics, geology of the area, you should go in the way of non-in-lock, SSST, and coherence or cross correlation, because then you don't have only your relative locations on the fault of the sequence, what happened, but also your faults are very well located in space, because you do also the absolute location of these events. Also, HypoDD could be quite computationally heavy because you need to have all these calculations that are done, and it could take much longer to get some results. Okay, so now that we understand these simple steps, what we need to be careful and what we can use to do this, we will look at some examples that we did in the last few years using these methodologies. So first we need to ask ourselves why does this matter? Why we want to do this? Why are we interested in locations in hundreds of meters, in the scale of a couple of hundreds of meters? Why are we not satisfied with more? So when we relocate the catalog with precision, we just discussed, we can easily. Sometimes we can identify previously unrecognized active fault segments. We can delineate the depth extension of such faults in 3D space. But at the end, if we have very well located earthquakes, we can talk about the rupture lengths that are possible on such new faults. We can see how the faults are segmented, and we can also estimate the maximum magnitude that is possible on such fault that was previously unrecognized. So all these things can reduce spatial uncertainties and can be inputted into our seismic hazard estimation, which is something that we want to do. Okay, so let's look at a few examples. This is example of 2019-2020 Puerto Rico sequence. There were 3 strong earthquakes that did quite a lot of damage, magnitude 5.7, 6.4, and 5.8. And if we look at these locations that were given from the seismological survey here, we can see some cloud of seismicity, and we cannot really discuss some geometry of faults here. So what we did, we used this non-log SSST coherence relocation methodology, and you can see this is now our final locations. And we were able to see that 2 out of 3 activated faults in this sequence were previously unmapped. So they were not detected by geologists. They were not detected by some geophysics. So they only showed up on relocation of seismicity. And we also saw that maybe this subduction zone south of the island basically still is active, even though it is thought as non-active currently. It is also a nice example because all the stations are on the island here, and nothing here in the sea, but the locations had very small errors. The results were very nice because of using of this absolute location, which also works quite well offshore. Now let's look also at the Slovenian example. So this is a low strain region, so everything is very slow, not many earthquakes that we get. And our modern seismic network started in 2004, not before. The largest earthquakes in the last 30 years were magnitude 5.6 and 5.2 that happened here. And as you can see, the one in 2004 is when the seismic network started to operate. You can see it here as these stations that are currently running in Slovenia. Historically, we had a magnitude 6.4 here along this Idria fault. We don't know much about it, but we know from historical sources that it happened. And then in 1895, a magnitude 5.8 somewhere here that damaged the capital of Slovenia, Ljubljana. There were quite a lot of damage. So it's good to know where the earthquake happened, because up till now, we don't know this. So the workflow that we did is classical non-log SST coherence. Then we used some focal mechanisms to try to find the best suitable faults from our relocated seismicity. And we used a 3D velocity model of the region and a large catalog of around 44,000, almost 45,000 events recorded in the 20 years between minus 1.5 and 6.4 magnitude, local magnitude. And we said, okay, we will only try to locate those events that have at least 10 phases. So they will be very well constrained in space. So after the location with non-log SSST and correlation, these are statistical results. We were able to relocate 25,000 events between magnitudes -1 and 6.4. And you can see that, let's say, azimuthal gap, this is what I was talking at the beginning, majority is between 60 and 120 degrees. So these are all well sampled by stations. The vertical errors are very small, so majority of events have vertical errors less than 1 kilometer. Minimum horizontal uncertainty is now 1 kilometer, and the maximum horizontal uncertainty is 2 kilometers. So all of our events, all of these 25,000 events are very well located. And now the picture of our relocated seismicity looks something like this. The purple lines represent active faults in the region, and these colored dots are all the earthquakes that we relocated. And quickly we see that in some cases they fall directly on the active faults, and in some cases, let's say here, it's not so obvious. We have some faults here, but a lot of seismicity is happening off the known active faults. So there were some surprising results. Here on the left, you can see the initial catalog. These red dots represent the 1D location done in real time, and there is a cloud of seismicity, but then after the relocation, this cloud collapsed into these lines that you can see here. So basically what we see here is a bottom of an active fault and the top of the active fault. So you can see that the results are actually quite good. And let's look a bit more in detail for this fault. So you can see on this map, the purple line represents the mapped active fault in this region, but you see that the earthquakes are completely, geometry of these earthquakes tells a different story. So we looked at this more in detail, and we even see on the velocity model cross-section here in this direction that our velocity model is shifted directly where this seismicity is going on. Even the focal solutions are here reversed. So basically we are mapping a reverse active fault in a region where this kind of faults are not existing in the known, in the geological maps. So this is one now a candidate for this earthquake that happened 1895 in Ljubljana. Ljubljana is very close by. And basically we are looking at the blind thrust that we did not know before because there is nothing on the surface. And this is something we will be studying further in the future. So a simple statistical test for this seismicity that I showed you in that area. If we just take these purple lines as active faults, we can see that we have like 287 events that do not fall on any of those faults. But if we introduce a fault with reverse mechanism and this strike as delimited by the seismicity, we can see that now less than 200 events are unassociated, and this new fault takes a huge amount of events. So this is how we recognize that this is nicely oriented. The geometry of such fault is nicely defined by seismicity. Another example is here in southeast Slovenia that I said. So we have these active faults on the map, and the seismicity is not related to any of those faults. And if we look at cross-section in this direction, we see that these earthquakes are on a line. Even the focal solution of this sequence here tells exactly the same story. So there is a fault present with this dip. It has a reverse mechanism, and even the velocity model has a change in the shape beneath this thrust. So this is now our interpretation that we don't have this reverse strike slip faults that you can see here, but a large thrust over all this area. Again, the same statistical analysis shows that if you introduce this kind of thrust underneath this basin, we lower the number of unassociated events, and such thrust takes a majority of events. So we can say, yes, something is going on there. Okay, so some final thoughts. Why is this important? So on the left side, you can see ESHA map of, so seismic hazard map of Slovenia, which was done in 2001. And to create this map, they only used seismicity. So they did not relocate seismicity well. They did not look at faults that are defined in geology. And you can see we have some red bullseyes here and in Ljubljana and here. But then in 2021, also relocated seismicity started to play a role in ESHA estimation for Slovenia, and also mapping of active faults. So you now see that the shape is kind of different. So here, before, this area was not so, the hazard was not so high, but now actually is the highest. And also for this southeastern part, it extends the high hazard slightly more towards southwest than it did before. So we want to have as good information on where the active faults are, because this is then at the end of the day all the input that we can use for seismic hazard analysis. If we can locate earthquakes, very nice. We can see that maybe we have in some area blind faults, which were before just like in PSHA we call this. Sorry, some spatial clusters. I mean that we cannot really say what kind of fault there is, but as soon as we introduce a fault there, the hazard will be much better quantified in that area. So that's why we need to do this kind of things. If we don't, we will not get the real hazard estimations. We will get lower or maybe even higher. So we need to get as much physically supported stuff into our models to be better informed about the hazard and risk. So, okay, thank you. And if you have some questions, please ask. I have time.
Well, thank you, Blaž, for this amazing talk. So the floor is open for questions. You can unmute yourself and ask Blaž a question you may have. Blaž, I will start with a quick one. So how does this really works in the context of really few stations within a network, say in the case of most African networks and with detection? I mean, we have very few stations within local networks. Does this really method still works?
Yes, I mean they do, of course. But if you have a sparse network, the first thing that you will know is that you can only detect certain earthquakes. Normally, you can your magnitude of completeness will be, I don't know, 2.5, 3. But to really go into the mapping of active faults, the magnitude of detection needs to be much lower, because then you get many more events. But the location steps, they will work fine. I mean, if you don't have a very dense network, but your earthquake is detected by all the stations in that area, and if you use Nomlin-Lock with these SSST corrections, it will give you quite good probabilistic location of that event. If it's large enough, you can get the focal solution, and this is already much better than nothing. So the nice thing here is this SSST corrections that even if you use 1D model will give you much more constraints on the results than if you don't. I mean, the test that I did for Slovenia is that in first step, I relocated the same events in 1D and 3D results. I mean, using 1D and 3D velocity model, and the final results are quite comparable. 1D initial model was not much worse than a 3D velocity model as an input. So even if you don't have a 3D velocity model, the SSST will give you good quality results. Yeah.
Okay, thanks. Any other question, please do ask.
Yes, in the chat, someone says they have 2 questions. So okay, so the first question is, did we make some additional checks to ensure that all the events detected by machine learning technique are earthquakes? So at my institute, we are currently, I mean, one coworker is working on this. So he's trying to implement machine learning as the quasi-real-time operation. So basically, we will do this when we will analyze last day of seismicity. A person will go through all the time, so all the detections during this time and pick the phases, and then run the machine learning algorithm and compare the results. So we will know if this is done or not. I mean, if this works as we want or not. But then in the literature where people are discussing this, yes, they also always check to get some initial feeling, are you doing this correctly or not? But yes, I mean, if you go into detection of earthquakes with machine learning, at least at the beginning, before you get some information, understanding of your region, it's better to do some checks. I mean, until now we did this just visually, but you can simply compare your, I don't know, let's say STA, LTA detections to your machine learning detections. And then the second one, oh, okay, no, well, there is, I will go one by one. Okay, some questions by Hassan, some questions about nonlinear lock SSST. Okay, so what is the grid size that we used for a Slovenian dataset, and how the grid size affects the location, and how sparse grid, say 5 kilometer to comparing to 0.5 kilometer. So for Slovenia, the grid size was 2 kilometers. I tried with 5 kilometers. Yes, so first I tried with 5 and then I went to 2 kilometers, and I did not go lower because I was limited with compute power. And yes, I mean, it's much better. The 2 kilometer grid is better, but this brings a lot of additional compute together. So let's say for this 25,000 events, it took my computer, it's 16 cores, it took like 24 hours to get the locations, or 48 hours, yes. So if I would go to 0.5 kilometer grid, I don't know if this would be even possible on such a computer. It would be possible to do the SSST, yes, but the cross correlation, no, because this would most likely eat all the RAM and all. It would just stop working nicely. So maybe if you go to this very low, let's say 0.5 kilometer grids, it's better to just look at a single sequence, not on a regional scale like I did. So for regional scale, I don't know, the 2 kilometer in my view is okay, because I can match this directly to known faults, and the match is quite okay. So I think it's reasonable. But if I would be interested in some specific swarms or aftershock sequences that I have in my area, I would go, yes, even lower, to maybe 0.1 kilometer. But then you are really limited by the number of events that you can look at. I hope this is okay. Have you tried another associator? Based on our experience, different associators give different detectability. Yes, of course. So during real-time monitoring of seismicity in Slovenia, we use some custom-made associator, a simple one, which is more than enough. It gives you very well associated phases. Sometimes we see problems with aftershocks, and we manually remove some phases and put them in to some other event. But when I was working with machine learning examples, I mean, I did not do a lot. I just a couple of times. I always use this gamma associator because it was so easy to set up and it was very fast. So I don't have here more information if I would use some other one, but there are a lot of these associators available online, so everyone can try what's the best for their region. I would say that it depends. I mean, what you're looking at. If you are just looking at normal seismicity, it does not make sense to really go very details here. But as long as you're working with some aftershocks or swarms, this is also something that should be tested. But the same colleague that I said before that is working on implementation of machine learning at our institute, he said that the gamma associator was the one that did work best for our cases. Okay, another one. Yeah, okay. Is it possible to use this method also for offshore earthquake relocation? If yes, how much it can be possible, vertical and horizontal? What are the horizontal and vertical errors? So as I showed in the Puerto Rico example, this is the case. I mean, these were offshore events, but still not so far away from the closest station. So if you would be really interested in those, I don't know, mid-ocean regions, very far away from your stations for large earthquakes, there are papers that show that using SSST gives you much better results. I don't remember the title of the paper now. The name of the author is Nima, but I don't remember the last name now also. But they show that yes, offshore events relocated with SSST are much better constrained. Horizontal errors are much smaller, but I'm not sure about the vertical errors because having events so far away, you need also to look at different phases to get better vertical constraints. So this is what I can answer. No problem. Okay, Daniel, I think this is all from the chat. So if
Yeah, I can.
Yeah, yeah.
Can I ask
Please go for
about?
it.
Yeah, I wanted to ask about the algorithms you are using. Are they open source tools or these are proprietary packages that are used at your institute? And if they are open source, are they Python packages that are already existing in PyPy or? And you were talking about the data or the data processing or the grain size you use. If you do fine grain or coarse grain, it chews up the RAM, and also you have 16 cores of CPU processing power, but you cannot go way low like high resolution analysis. So I wanted to know about how these programs that you are running on the amount of compute resources you have. Are they running in parallel or they are running in serial, or like it's not disclosed because there's a proprietary software? Or just wanted to know.
okay, so yes, thanks. So all the things that I showed here, this is all open source. Okay, I mean, let's say at our institute for daily monitoring, we use the software package Antelope, which is not, I mean, it's open, but you need a license and so on. But because we are a national institution that, these things needs to work fast and without some problems, we use this. But then the relocations that I showed you, this was done by using nonlinear lock, which is completely, open to use. It's written by Anthony Lomax, and he's very happy also to help in cases. And then let's say the machine learning algorithms, the one that, so let's say where this picture comes from, this is described in this paper, and this paper is also on the software they use for the detection and relocation of these events. So this is part of Pyroco package, and it's open source. Everyone can use it. They offer even a few different models that you can use for detection of phases, machine learning models. So it's also very simple to use. I mean, they have a website where you can see how to set it up. It will work on a laptop. It's not a problematic thing. Earthquake detection, let's say for STA, LTA, this is very simple thing. As I said at the beginning, this even runs on the station themselves, those that are triggered. But let's say these machine learning approaches, yes, it's computationally more expensive, but not so much. I mean, you can basically run few stations, detection and location of few stations on a laptop. You don't have to have a supercomputer for something like that. Let's say for the problem here is if you want to relearn your model, with your own data sets, this is what is computationally very exhaustive. Yeah. Okay. And then for the nonlinear lock SSST thing that I did from Slovenia, so those 25,000 events that I was able to relocate, this was, like I said, 2 days of computation on 16-core CPU with, I think, 60 gigabyte of RAM. Okay. So in terms of modern computers, nothing so fancy. But if you don't do the correlation step, or if you don't do the SSST, if you do just the nonlinear lock part, it's very fast. It will, okay, I don't know, 1 hour and you have 25,000 events. But as soon as you do this SSST, it's slightly more computationally expensive. But it should not be, I mean, really depends on the size of the grid. Yeah, of the grid.
Yeah.
In my experience, I mean, when I went from 5 kilometer to 2 kilometer grid, I mean, this really made a big difference. It went from a couple of hours to 2 days of compute.
Yeah. So how does the data comes in the data formats? How do you store your data formats? Are they binary? Are they text? Are they like special in some cases? I don't know.
Yeah, so at my institute, the data comes in real time, and then from all the stations that we have, and is then saved as mini-SID binary files in our archive. And let's say this machine learning software, I mean, it reads mini-SIDs. You just give them insight, and it will.
Perfect.
Yeah, it will really. It's really simple to use. I mean, if you will go check this paper, go to their website, download it, and you will have it running in 1 hour. It's very, very simple to set up.
All right. Thank you.
Yeah, no problem.
Any other questions? So I think everyone is happy. Blaž, thanks once again for this very nice presentation. And thanks everyone for joining us today. See you next month.